Hey everyone, welcome back to Trigonometry. This is going to be lecture 3 of the course. In this section we're going to talk about right triangle trigonometry. So we started last time with a definition of the trigonometric functions that used the unit circle as the basis. Now what we're going to do is we're going to think about what the trig functions can mean in the context of right triangles. So let's go ahead and get started. And we'll call this section 1.3, right triangle trigonometry. So let's start with kind of stepping back and examining the unit circle definition of the trig function. So we start with a unit circle. Okay, and again, this is obviously a unit circle, so it's centered on the origin of the xy coordinate system. Okay, and so let's say we have a ray, right, and we'll call it P, and again we'll say that's the point xy, right? And so we know that what that means is that this is the x value and this is the y value. Okay, so this we talked about last time. Okay, and so for a triangle like this, we could say that the angle theta is there. Right, so we'll think about this angle theta that is sweeping out a portion of a unit circle as we've depicted here. Right, so here, of course, you know, the radius is 1, right? So this is the radius, so that's 1. And the point P equals xy is going to have a height of y, right, from the x-axis, and a length x from the origin along the x-axis. Okay. So clearly you can see this, and you know that this is going to implicitly form a right triangle, right, within this construction. Right, so another interpretation of the trigonometric functions can be based on this right triangle, right? And so just to kind of make that explicit, let's pull the triangle out. And so let's say we've got, you know, this theta, we've got an x on this side, a y on this side, and 1 up here. Okay, and so we can think of the trig functions in the context of this triangle. We can think of the trig functions in the context of this right triangle. Okay, and so that being the case, we would say that the sine of theta, remember, is equal to y. The cosine of theta is x. The tangent of theta is y over x, right? The other ones, the cosecant, these are all the reciprocals, right? So that's 1 over y, and then the secant is 1 over x, and the cotangent is x over y, right? Okay, and so this is, I mean, the way we've kind of framed it up right here, it's almost like just a rehashing of the unit circle idea, right? But notice that this can be sort of generalized. We can generalize this, right? So let me write this. So this can be generalized, right? We don't have to think about this simply from the standpoint of a unit circle. Right, we could say let's draw our unit circle triangle here. Let's redraw it here. So you've got 1, you've got your x, and you've got your y. Let's just relabel this thing a little bit. Let's draw another triangle. Right, so again, you've got your theta, and let's say this is an ABC triangle. Okay, and so this will be side little a, this is side little b, and side little c. So just in case you're not aware of what's going on here, the angles, the vertices, are labeled with the capitals, and then the side opposite is labeled with the lowercase. So this is vertex A, and so the opposite side would be little a. Okay, and then we labeled this angle theta. Okay, and so using this triangle, using this triangle alongside the pattern that we established with the previous. So we'll say alongside the unit circle pattern, what do we get? Well, we have this sine of theta, right? We saw that the sine of theta was equal to y, right? And I'll just expand on the sine of theta so we can see what's going on here. So we saw that the sine of theta is equal to y. Well, really, we can think of that as y over 1, right? If you look at this triangle, it's this over this. And so what it really is, it's the side opposite theta. So we'll write opposite. It's the opposite side divided by this side here, which is called the hypotenuse. The hypotenuse. Okay? And so it's the opposite side, this side here, divided by the hypotenuse. Okay? And so in our new triangle, it's a over c. Okay, what about the cosine? Well, we saw that that was x, and so we can think of that as x over 1. And so that's actually the side that's adjacent to theta, right? Meaning it's connected to the it's one of the sides that contributes to the angle theta. In this case, it's the initial side of theta, right? So we just refer to that as the adjacent side, right? So it's the adjacent side divided by the hypotenuse. Okay, or in the case of this triangle, it's b over c. Okay, and what about the tangent? I'm going to just do it over here because I want this on the same page. So the tangent of theta. Well, in the unit circle definition, it's y over x, isn't it? Right, but then what is y? Y is the opposite. And what is x? X is the adjacent. Okay, and so it's really a over b. Okay, and so in this case, the trig functions, and we'll do the other ones as well, but let's just kind of start with these three. The trig functions are defined not as points on the edge of a unit circle, but instead as the ratio of sides of a right triangle, right? So the sine is the ratio of the opposite side to the hypotenuse. The cosine is the ratio of the adjacent side to the hypotenuse. And the tangent is the ratio of the opposite side over the adjacent side. Okay. So let's take a look at all of these together now. Okay, so we said the sine of theta is equal to opposite over hypotenuse, which we will label as a over c. Let me put the triangle on here as well. Okay, so you got your theta, and then a, b, c, little a, little b, little c. Okay, so sine of theta is opposite over hypotenuse, and so it's a over c. Cosine of theta is adjacent over hypotenuse, so it's b over c. The tangent of theta is opposite over adjacent, right? So it's a over b. And then the other three are going to just be the reciprocals again, right? So that reciprocal relationship still exists here naturally. So the cosecant is really going to be the hypotenuse over the opposite side. Hyp over op, so c over a. The secant of theta is hyp over adjacent, so it's c over b. And the tangent of theta is adjacent over opposite, and so it's b over a. Right? So that's the definition of the trigonometric functions in the context of right triangles. And you can see how, really this definition is based on the idea of a triangle embedded in a unit circle like this, right? We saw that in the initial picture, right? So you've got this implicit triangle with an x side and a y side, right? And that's where we got this triangle from. And then the pattern that we use to define the trig functions in the context of the unit circle can be extended and generalized to any right triangle. Okay. The key here is that this is a right triangle. It's got a 90-degree angle. Okay. Right. So theta can be any angle under the sun, but this has to be a 90-degree angle. Okay. Okay, very good. Right? And so you may be thinking to yourself, how in the world will I ever remember this definition? Well, this one's actually pretty easy to remember. There's a very kind of famous mnemonic device that people rely on. So to remember this, you can use SOHCAHTOA. SOHCAHTOA. Right? So that's the that's the way to remember this. And so what is SOHCAHTOA? Well, you got the S, which stands for sine, and the O, which stands for opposite over hypotenuse. Then you have the C, which stands for cosine, and the A, which stands for adjacent over hypotenuse. And then you've got the T, which is the tangent, and the OA, which is, of course, the opposite over the adjacent. And so this is what people use to remember this. So the SOHCAHTOA. I use this to this day. I mean, I don't have the trig functions hardwired. I think the fact that this mnemonic device exists makes it impossible for me to ever memorize it. All I remember is SOHCAHTOA, and it just pops right out of there. So this is how people tend to remember the right triangle definition of the trig function. So SOHCAHTOA. Okay. So that's what we want to kind of start with that, and we want to move from that into, we're going to kind of shift gears a little bit, but we'll come back to this with some great examples in a moment. But before we get to those examples, we want to talk about the Pythagorean theorem. And this is probably the most famous theorem in all of mathematics, probably. I don't know what would be more famous than this one. So the Pythagorean theorem is a theorem about right triangles, and so a lot of the examples we're going to do and a lot of the right triangle trigonometry that we're going to rely on is going to take into account and use the Pythagorean theorem. So let's talk through what the Pythagorean theorem says. So starting with a right triangle, okay, let's say that's the right angle there, not very right looking. Let's draw just a little better. Okay. And let's label it A, B, C. All right, so the two legs, these are called the legs. These are the sides adjacent to the right angle. Those are called the legs. And then the hypotenuse is the side of the triangle that's opposite the right angle. Okay, so here's the theorem. Given a right triangle with legs A and B and hypotenuse C, right? So given a right triangle with legs A and B and hypotenuse C, the lengths A, B, and C are related to one another as what? Well, A squared plus B squared equals C squared. Okay, right? So the idea here is if I take this length, whatever this side is here, A, I square that length, I get a number. Then I take this side here, B, and I square that, I get another number. Now when I add those two squares together, they're going to equal this length squared, right? And so these right triangles have this sort of really fundamental relationship between the length of the three sides. Okay, so let's see how this can work. How can this be useful? Let's find the length of the hypotenuse C for this triangle. Let me draw this out. And, you know, the triangles may or may not be drawn well. Let's say we've got a theta over here, and we've got a right triangle, or right angle there. And let's say that this side is 12, this side is 5, and then the hypotenuse is unknown. What can we do? We want to know what C is. Well, a squared plus b squared equals c squared, right? Plug in the numbers. So a in this case we'll say is the 5, right? So 5 squared plus 12 squared equals c squared. Okay. And what is 5 squared and 12 squared? Well, that's 25 and 144. Okay. Right. And so what does that mean? Well, that means c squared is equal to basically 25 plus 144, which happens to be 169. Okay, so c squared is 169. Now, how do I figure out what c is? I don't care what c squared is. I want to know what c is. Well, I can take the square root of both sides here. Plus or minus, right? And so what I get here is that c is equal to plus or minus 13. So 13 squared happens to be 169. Okay. And so it's either positive 13 or negative 13. And so because we're talking about a right triangle, and lengths have to be positive, the only interpretation here that makes sense is the positive one. Right? So here the positive value is the only one of relevance. Okay, so therefore C is equal to 13. Okay, excellent. Let's try another example. Now what I would encourage you to do is, once I state the problem, pause the video and see if you can figure this one out yourself. So given the following right triangle, we want to evaluate the 6 trigonometric functions trig functions for the angle theta. Okay, and so then what is the triangle? Well, the triangle we'll say looks like this. It's a right triangle, of course. Okay, so I've got my theta, and let's say that b is equal to 2 square root of 2, a is equal to 1, and c is unknown. Excuse me. So can we figure out what the 6 trig functions are? Well, definitely, but we first have to figure out what c is. So we have to use the Pythagorean theorem here, right? And so a squared plus b squared equals c squared. Okay, and so that is what? 1 squared plus 2 square root of 2 squared equals c squared. Right, just plugging in those numbers. Okay, and so what do I get here? I get 1, that's 1 squared is 1, plus, now what is this? This is like 2 squared, which is 4. And then the square root of 2 squared is 2. So it's like 4 times 2. Right? So I get 1 plus 8 equals c squared. Right? And so c squared is equal to 9. Okay? And so that means that our c is equal to the square root of 9, which is 3. Right? Now technically plus or minus the square root of 9, but we know that we're talking about triangles, so the positive one is what we want. Okay, and so that means c is equal to 3. Okay, so that's the first part of the problem. Now we just have to apply the definition of the trig functions to this right triangle and finish the problem. So let's do that. So let's redraw the triangle so we can reference it here. So I've got my theta, my right triangle. I've got 2 square root of 2, 1, and 3. Right, so notice here my hypotenuse is not 1 as it would be if I were talking about a unit circle. Right. So let's see what everything is. So the sine of theta, so remember SOHCAHTOA. Okay, so the sine of theta is equal to opposite over adjacent. And so that's equal to 1 over, oh, sorry, opposite over hypotenuse. What am I writing here? O over H. And so that's equal to 1 over 3. So there's the sine. The cosine of theta is equal to the adjacent over hypotenuse. And so that's 2 square root of 2 over 3. And the tangent of theta is equal to the, the opposite over adjacent. And so that's equal to 1 over 2 square root of 2. Okay. And so we can rationalize that. Let's bring that down here. So the tangent of theta, I'll rewrite it here, is equal to 1 over 2 square root of 2, which is equal to 1 over 2 square root of 2 times the square root of 2 over the square root of 2. And so up top I get the square root of 2, and down below I get 2 times, and this is basically square root of 2 squared, isn't it? And so that's 2 times 2, so I get over 4. Okay, so I've got that. And then the cosecant of theta, that's going to be hypotenuse over opposite, really the reciprocal of sine, so that's just 3. Just kind of put all the work in there so you can see that. And then the secant of theta is hypotenuse over adjacent, and so that's 3 over 2 square root of 2. Okay. And we'll just leave it like that for now, but you could rationalize that as well. And then the cotangent of theta is 4 over square root of 2, which we'll leave like this as well. But you can take it as an exercise to reduce those or to rationalize them. Okay, right, so there we go. So now we are off and running with both the Pythagorean theorem and also right triangle trig. Okay, so we have some sense for how the trig functions can be derived for an angle formed inside of a right triangle. Okay, all right, and so what we're going to do is we're going to use, what we're going to do next is we're going to use right triangle trigonometry to identify some more exact values. Okay, so let's remember what we've done so far. Let's remember what we've done so far as exact values go. We know the exact values so far. Let's draw the circle. So, and I'll put the angles in here. We've got 0 and pi. We know those. We know the exact value of the trig functions at those two angles. We've also figured out pi over 2 and 3 pi over 2. We know those two as well. Right, so these all are based on 0 and 1. Right, so this is the point 0, this is the point 0, 1, this is the point 1, negative 1, 0, and so we could use that in the previous lecture to find the exact values of the trig functions. We also looked at pi over 4, right, so this guy here, and then by extension I said you could go ahead and figure out the others, so this would be 1, 2, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We figured out all of those. We mostly figured out this one, but we said the exact same reasoning could be applied to get these other three. Okay, and so now what we want to do is we want to look at pi over 6. Okay, and so pi over 6 is 30 degrees, so it's actually right about here. Okay, so we want to figure out pi over 6. We want to look at exact values of trig functions at pi over 6. Okay, so that's next. Okay, and so again, we've identified the exact values at pi over 4, and so pi over 6 and pi over 3 are two other very frequently used. So pi over 6 is here, pi over 3 is going to be like right about here, and we're going to look at those two today. Okay, so let's start. Let's go ahead and get started. I'll flip this to a new page so we can derive this nicely. So we're going to start by considering an equilateral triangle. Okay, equilateral triangle. Let's see if I can draw it well. I probably won't. This is a terrible drawing already. All right, what? Equilateral triangle means all of the angles and all of the sides are the same. And so this is a bad drawing, but let's just roll with it. So let's say this is 60 degrees, 60 degrees, 60 degrees. And we'll just say that this is 2, 2, and 2. Right? So this is an equilateral triangle. Equilateral triangle. Right? And so all that means is all angles are 60 degrees, right? The length of the sides are arbitrary, but however long one of the sides is, the other two sides have to be the same length, right? But the angles are locked in at 60 degrees. Okay. Now what we want to do is we want to drop a perpendicular from the top of the triangle to the lower edge. So we're going to drop a perpendicular from the top to the lower edge. Okay, and so what do we mean? We're just going to do one of these here, right, and get a right angle. Okay, so I'll just draw it down here. And so when we do that, what's the dimensions of our triangle going to be? Okay, so you'll have a right triangle, hence, right, because dropping a perpendicular means literally dropping it perpendicular to this leg, which means right angle. And so the whole length was 2. It's now going to be 1 on the bottom. And the height, we're not sure about, but we know the hypotenuse here is going to be 2. And we know the angles. This is 60 degrees. And if this is a perpendicular, then that's going to have to be 30 degrees, isn't it? Okay, so we've got this new right triangle. And let's go ahead and figure out what this side here is. And so we can do that using the Pythagorean theorem. So let's identify the missing side. Okay, and we'll say the missing side in this case is, we'll call it B. Okay, so a squared plus b squared equals c squared, right? And maybe we know a and c in this case, right? So we've got 1 squared plus b squared equals 2 squared. Okay, and so that means b squared is equal to 4 minus 1, or 3. Okay, and so that means b is equal to the square root of 3, right? Just kind of going through, doing the algebra there, solving for b, and at the end here, b squared equals 3. You just take the square root of both sides. Okay, and so that means our triangle is 2, square root of 3, and 1. All right, so we've got this guy. Okay. And so let's start by letting theta equal 60 degrees. Right, so theta equals 60 degrees, that's going to be pi over 6. That's the pi over 6 that we're interested in, isn't it? Okay. All right. And so given that, we can quickly figure out what all of the trig functions are here. So wait 1 second. So it's pi over 6. Okay, I gotta make sure. Let me double check this. So 60 degrees times pi over 180. That's pi over 3. I'm sorry about that. Make sure that's right. Okay, so 60 degrees is the pi over 3 read. Okay. All right, so we'll start with this, and so we can just kind of read them off, can't we? So sine of pi over 3 is equal to, remember your SOHCAHTOA, right? So it's opposite over hypotenuse, so opposite over hypotenuse, so it's the square root of 3 over 2. The cosine of pi over 3 is adjacent over hypotenuse, so it's 1/2. And the tangent of theta, right, the tangent of pi over 3, that's going to be opposite over adjacent, and so that's square root of 3 over 1. Okay, so we've got sine, cosine, and tangent. And then the other three are just the reciprocals, right? So the cosecant of pi over 3 must be 2 over the square root of 3, right? Which is equal to 2 square root of 3 over 3 when you rationalize the denominator. And the secant of pi over 3 is equal to 2, okay, 2 over 1. And the cotangent of pi over 3 is equal to 1 over the square root of 3, which is the square root of 3 over 3 when you rationalize it. Okay, and so there we have the 6 exact values for theta equals pi over 3. And we could do the same exact thing for the 30-degree angle, right? We just have to reorient ourselves here. So let's next look at theta equals 30 degrees, which is the pi over 6. Okay, and so here we'd have sine of pi over 6, right? The sine of pi over 6 is equal to, again, it's going to be opposite over hypotenuse, and so the opposite here is going to be 1, and the hypotenuse is 2, right? So it's 1/2. The cosine of pi over 6 is equal to the adjacent over hypotenuse, and so remember, if 30 degrees is the angle, the adjacent side is square root of 3, and the hypotenuse is 2. And then the tangent of pi over 6 is equal to square root of 3 over 3, 1 over the square root of 3, basically this over that, rationalize. Right, so you've got those three. And then the others are just the reciprocal again. Cosecant of pi over 6 is 2. Secant of pi over 6 is 2 over the square root of 3, which is 2 square root of 3 over 3. And then the cotangent of pi over 6 is 3 square root of 3 over 3. Okay. Oh, otherwise known as the square root of 3. Yeah, I guess those cancel, don't they? Okay. All right, very good. Okay, and so there we have more exact values, right? So if I flip back a page, we now know these two and these two. And so implicitly, the exact same reasoning can be applied to this angle and to that angle, to that angle, that angle, that angle, and that angle. And so this gets us very close to having all of the angles that are immediately important to our study of trig. Okay, and so in the next lecture, I'll introduce kind of a you can think of it as kind of a cheat sheet, a unit circle cheat sheet, and I'll introduce that in the next lecture. So next lecture, I will introduce a unit circle cheat sheet. Okay, we can use the cheat sheet when we're doing more complex trig problems where the exact values are not the point of the problem, right? Where implicit in the background is that you can find the exact values for these angles, right? So now that we've derived them and I've shown you where they come from, it's fine to reference them. I don't expect people to memorize them. You're certainly welcome to memorize them if you like, but I don't know if it's practically important to memorize them. Okay. All right, so just one more quick thing here for this section, and that is complementary angles. So let's define that. So two positive angles are called complements. They're called complements if their sum is 90 degrees, otherwise known as pi over 2. So for example, pi over 3 and pi over 6 are complementary. Right, and why is that? Well, because when I add them together, right, how do I add this? Well, I got to get a common denominator, so that would be, 2 pi over 6 plus pi over 6 equals 3 pi over 6, which is pi over 2, right? Right, so just when I add them together, I got to blow this denominator up, right? That becomes that. Okay, so those two angles are complementary. Okay, and sort of equivalently, you could say 30 degrees and 60 degrees are complements. Right, obviously 30 degrees plus 60 degrees equals 90 degrees. Right? So, notice that the sine of theta, which is equal to opposite over hypotenuse, which let me draw this triangle here. If I draw this kind of right triangle, say I've got my theta here, and I've got my A and my B and my C, and this is a right angle. So if this is theta, right, and this is 90 degrees, then what is this one? Well, the whole triangle is 180, isn't it? The whole triangle is 180 degrees. And if this is 90, then these two together have to be 90, right? And so this one plus this one is together, they're 90. Oh, I'm so sorry. So I've got my triangle here, right? All three angles are 180 degrees. This is a 90 degree angle, and this angle is called theta, right? So if all three are 180 degrees and one of them is 90, then these two have to be 90. They have to add up to 90. And so if this is theta, then this one here is automatically 90 degrees minus theta. Okay? Right, now why is that? Well, the whole thing has to be 180, right? So you've got 90 down here plus theta plus what this guy here, which I'm calling 90 minus theta. Right? And so what does that equal? So I've got 90 plus theta plus 90 minus theta. And so I've got 90 plus 90 is 180. Theta minus theta is 0. Right? And so you can just kind of see algebraically that if I have a right triangle and one of the angles 90 and the other one's labeled theta, an appropriate label for the third angle is 90 minus theta. Okay? And so if I've got the sine of theta equal to opposite over hypotenuse, which in this case is A over C, then cosine of 90 minus theta is equal to adjacent over hypotenuse, which is A over C as well. Okay? Right? So the sine of theta is opposite over hypotenuse, so A over C. The cosine of this other angle, 90 minus theta, is adjacent over hypotenuse, which is, again, A over C, right? So these two are equal. So in general, if two angles are complements of one another, the sine of the one is equal to the cosine of the other. So in general, let me write this down. In general, if two angles are complements, right, if they're complements of one another, the sine of one is equal to the cosine of the other. Okay, right, and so this leads to a very nice set of identities called the cofunction identities. This leads to the cofunction identities. Okay, then what are those cofunction identities? Let me write them out. Okay, so you've got the co-function identities. What are they? Well, the sine of theta, which is the one we just did, is equal to the cosine of 90 degrees minus theta. Okay, and so also cosine of theta is equal to sine of 90 degrees minus theta. Right, theta and 90 minus theta are complementary angles, right? Now it turns out that these can be extended to the other trig functions as well. And so the tangent of theta is equal to the cotangent of 90 minus theta. And naturally the cotangent of theta is equal to the tangent of 90 degrees minus theta. And the secant and the cosecant are related as well. Secant of theta is the cosecant of 90 minus theta. And the cosecant of theta is the secant of 90 minus theta. Okay. All right. So let's see a practical example here. Let's see a practical example. So let's say if the sine of pi over 2, we know what the sine of pi over 2 is. It's 1, right? If it's equal to 1, then the cosine of 90 minus pi over 2, which is in this case pi over 2 minus pi over 2, is equal to cosine of 0, which is equal to what? 1, right? Okay, so that's that's a very simple one to see, right? So on the unit circle, just to remind ourselves where these are coming from, if this is pi over 2, right? So this point up here, the x and the y would be equal to what? 0, 1, and the sine is the y value, so that's where that comes from. Over here, what's the angle of interest now? Well, it's 0, right? So your point here, xy, is equal to 1, 0. The cosine is the x value, and so that's that one. Right, so they're equal. Right, we can do the same thing with the tangent. If tangent of pi is equal to 0, then cotangent of pi minus pi over 2, okay, is equal to cotangent of pi over 2, which is also 0. Okay. Okay. All right, so pi and pi over 2 are obviously coterminal, right? So there we have it, right? And so we'll leave it there. And we could say etc., right? You could see lots of examples of these. So these are called the cofunction identities, and they will come up from time to time, right? And so throughout the course, we'll be introducing little identities like this. And yeah, so okay, I think we'll leave it at that. And next time when we get together, the next lecture, we'll discuss trig functions, and we'll extend that to include basically any angle, right? And so we've identified trig functions for a lot of exact values for specified angles of importance. Now what happens with the rest of the angles? How can we find them? All right, and we'll leave it at there. So talk to you all next time. Take care.